What's up, guys, and welcome back to another episode of All the Nerdy Details. Today we're talking about drive shafts, and you better watch out because it's gonna get nerdy. In this series, we nerd out on the science and physics that play a role in just about everything. We dive into the way things work and examine the incredible engineering that goes into going fast. So today I wanted to bring up a topic that I have been struggling with on the Legacy. If you guys haven't seen the build video of the Legacy, go check it out. This is our H6 swap 2nd gen Legacy with a rear wheel drive conversion with a BRZ 6-speed transmission. One of the critical things on this project was the drive shaft, because there's no configuration where an R160 rear diff in a Subaru was paired with the 6-speed transmission. And the length of the transmission is different than the standard 5 speeds and 6 speeds for Subarus because its chassis is different than a BRZ and an FRS. Obviously we have some issues. So we had to build a custom drive shaft. This was probably the most frustrating part of the project and the most expensive because I had to learn my lesson the hard way. I'm teaching you guys in hopes that you don't waste your money having to build and rebuild a drive shaft because it wasn't built properly. Let's get started. At risk of looking like Mr. Engineering Explained, hope you see this, I had to break out the whiteboard to show you guys a little bit of what's going on here math-wise. I know it's super boring, but I already did the math for you, so you don't even have to worry about that. To start off, just to clarify, there's two different major types of drive shafts, which are stationary and dynamic. We are only talking about stationary drive shafts. The dynamic drive shaft is for something that has lots of suspension travel. The drive shaft actually moves in and out of itself with a slip yoke. Now we're talking about independent rear suspension cars that have a drive shaft that essentially stays stationary because the axle itself is not articulating. Let's start with a little bit of drive shaft anatomy. There's essentially 5 parts of a drive shaft. First off is the slip yoke, which is the splined end that goes into the transmission. Second off is the carrier bearing. If you have a 2-piece drive shaft, you have a 1-piece, there is no carrier bearing, which supports the intersection of the first part and the second part of the drive shaft on the body of the car. You have the U-joint, which is the joint that actually articulates to transfer your movement into an angle. And you have the flange yoke, that is the part that attaches to the differential flange. And then you have the drive shaft tube, of course, which is just a piece of steel or aluminum tubing that's attached to the yoke ends to essentially connect the whole drive shaft together. A lot of controversy. Why 1-piece versus a 2-piece? There's a couple different reasons, one of which being size constraints. The overall diameter of the drive shaft tubing is essentially what limits you from being able to span a certain distance safely. That's the problem with the Subaru, is that we have such limited size in there because it was meant to be an all-wheel drive car, not a rear-wheel drive car, to basically get our torque transferred all the way to the back. If we go to a 1-piece drive shaft, we would have to up the diameter a lot, which actually requires quite a bit of modification to the tunnel to make it fit, which was what I had to do to the Impreza because it does have a 1-piece aluminum drive shaft. The other thing is cost. When you go to a 1-piece drive shaft, you have to use lightweight material in order to reach your safe operating RPMs for that drive shaft. So a lot of people turn to aluminum and carbon fiber as materials for the drive shaft, because if you can reduce your rotating mass, you can increase the safe operating RPM that the drive shaft is able to obtain. But that's expensive, and we weren't trying to go expensive with this because I don't need the car to go 200 miles an hour, and I'm only transferring about 200 foot-pounds of torque to the rear diff. Really not that much. The other reason why you would choose 1-piece over 2-piece is just smoothness. 1-piece drive shafts tend to have a little bit more vibration in them overall because they're such a long length, and actually having a carrier bearing will decrease the amount of vibration transfer because you have that rubber isolator on the carrier bearing, so it does help a little bit with that. When designing a drive shaft, there's a lot of things that you need to take into consideration. One of which being the half-true critical RPM of a drive shaft. That is derived from an equation which I used a calculator. All these calculators can be found on Spicer's website. Spicer's a U-joint and Driveshaft, drivetrain manufacturer. And they offer all these awesome tools on their website to be able to go use. So if you ever want to design a drive shaft for a custom application, you can go on there and figure out what you need tubing wise to make it work. All these numbers are derived from a couple different constants, one of which being the type of U-joint, the series of U-joint that you're using. In our specific application, we're using a 1310 series U-joint from Spicer. The length of the drive shaft center to center on that U-joint, and the tubing diameter and wall thickness. And wall thickness matters because the wall thickness attributes to the mass of the drive shaft. I don't know what the formulas are. I just use the calculators because it was a lot easier that way than to try and figure it out. The half-true critical RPM of a drive shaft is essentially the halfway point in the maximum amount of rotation that you can get out of a drive shaft. Now obviously you'd never want to run a drive shaft at the full rotation capacity of it because you're right around the danger zone where a drive shaft can explode. And it happens too. Why is that important? Well, because at half the value, the drive shaft reaches a harmonic resonance. So you want to adjust the length and diameter of your tubing and wall thickness of your tubing to make sure that that half critical RPM number is way outside the cruising range of the car. So say the half-true critical range is right at 55 miles an hour. Now a lot of highway cruising speeds are at 55 miles an hour. So I'd actually want to adjust something in my drive shaft, adjust one of those constants, whether it be the length, the tubing diameter, or the wall thickness or material, to get that outside of that range. If you drive right past the half-true critical, you don't usually feel a thing. But if you sit at the half-true critical for too long and maintain that RPM, the drive shaft will start to pick up a harmonic resonance and do something called whipping. What is whipping? Whipping is when the centripetal forces applied to the drive shaft start to overcome the rigidity of the drive shaft itself and make it whip almost like a jump rope. So think of like skipping a jump rope. The drive shaft is essentially doing that when you've either sat at the half-true critical RPM for too long or exceeded the safe operating RPM of the drive shaft itself. And that offset of weight from the drive shaft bending will cause a serious vibration in the car and can actually cause the drive shaft to fail. Now, what is the safe operating RPM? So that is derived from the same formula and is just a percentage reduce of the absolute maximum RPM range for a drive shaft, and it just keeps you in a nice safe operating range for the drive shaft, because like I said, you never want to get anywhere close to the maximum because it could explode. It's essentially just a good guideline for designing any drive shaft so that you never get outside of an unsafe range for operation. I've done a little bit of calculations here to show you guys the issues that I had when I first designed this drive shaft. A little bit of backstory. I took my ends to a drive shaft shop. I told them how long that I needed it to be, and they produced me a one-piece drive shaft. I put it in, it vibrated horribly at 35 miles an hour, so bad that I couldn't even drive the car, and if I even tried to go highway speeds, it was just awful. Long story short, ended up taking the drive shaft back to the same people. They turned it into a two-piece drive shaft. It wasn't balanced properly after that, so I had to take it to another shop, and it was just a big mess. Our constants here, tire size. I'm running a 205 55/16 that's roughly 24.9 inches diameter of the tire. My final drive ratio, which is the final drive ratio in the differential, which we take roughly 4 times that, and that's what the drive shaft RPM is. So that is going to be 4.11, so it's a 411. On our drive shaft, the constants here, 1310 series U-joints, it's 2-inch diameter tubing, 0.93 wall thickness. Originally, when it was a one-piece drive shaft, it was 57.5 inches center to center on the U-joint. They're talking about the center of the U-joint cap to center of the U-joint cap for the length of the drive shaft. If I put those numbers into the calculator, it gets me a safe operating RPM of 2659 RPM and a half critical of 1970. Now if I convert that using our final drive ratio to actual miles per hour, I'm hitting the half critical RPM at 35 miles an hour, which means if I sat at 35 miles an hour for too long, I would get an awful vibration, which I was. The safe operating RPM is 47 miles an hour, which means I'm exceeding the safe operating RPM of the drive shaft just pulling onto the highway. That's bad. If you apply those types of vibrations for too long, not only can you risk damaging the drive shaft, but you can also damage the bushing that guides the slip yoke and the transmission, or you can destroy the roller bearings that support the pinion in the rear differential. All not very good things. Now watch this. Just taking it and converting it to a two-piece drive shaft, D1 and D2. D1 is the drive shaft length on the first section, and then D2 is the drive shaft length on the second section. So D1 is 28.5 inches and D2 is 29.75 inches. So getting the half critical and the operating RPM out of that, D1 is 6,000 RPM is our safe range. And now look at this. Because of the way that the drive shaft is designed, it actually takes our half critical RPM and shifts it above the safe operating RPM range. So there is actually no scenario, if we stay within that safe operating RPM range for this drive shaft, that we can even get a vibration from reaching the half critical. D2 gets us 6,000 RPM and 73.58. So obviously you want to take the worst off of the two numbers, and so our safe operating RPM gets us 108 miles an hour, which is well above any speed that I would need to go to this thing if I'm driving it on the road regularly. The other thing too is we won't actually hit the half critical RPM even at the worst section of the drive shaft till 132 miles an hour. I don't think I ever want to go that fast in the Legacy. I think we're gonna be okay. Now that we got our drive shaft back and it's balanced properly, we're gonna put it in the car and we're gonna go test drive it and see how it feels and see if all the vibrations have gone away now. So I got her out on our test road, cruising around 60 miles an hour, buttery smooth. So I think all of our vibration issues have been fixed and it is a much nicer car to drive. It's amazing how much of a difference it makes. That's physics in motion, my friends. Hey, thanks for tuning in, guys. I hope you enjoyed the video. I hope you learned a thing or two to maybe help save you some money instead of making mistakes like I did. So like, comment, subscribe. Stick around for the next one. Thank you.